we're just going to look at the extra stuff for higher level stats. Here. So the first thing is the correlation coefficient. So we mentioned that this is a number from -1 to +1 already in the ordinary level stuff. Basically, if it's +1, that means that the two variables are perfectly positively correlated. So something, if you had a data which was perfectly along a line in a linear way, then it would be +1. And if it was perfectly negative, so as this increased, that decreased, then it would be -1. But typically it would be, somewhere in between. What we're going to do here is see how to actually work out what the correlation coefficient is. And it's a bit messy or cumbersome, but there's nothing difficult there. So it's basically a 3-step process. If you have some bivariate data, so you have x's and y's, so imagine you had x1, y1, x2, y2, and so on, and imagine you had 100 pieces of data. In reality, or in practice, you're not going to be asked to work with 100 pieces of data, because that would just be too much hassle. But for this example, I'm just going to say 100 pieces. It doesn't change things particularly conceptually, how many pieces of data you have here. So the first step is, well, I'll do 1 because I've already written 1 here. It'd be confusing to use the same notation. Work out the means. So determine so if you had 100 things, you just add x1, x2, x3, all 100 values of x, and divide by 100. So, sum all the values of xi, and then divide by 100. Add all the values of yi, and divide by 100. Next, work out the standard deviations. So the standard deviation for x is you add xi minus the average value of x and square it. So you add that for all the different values of I, and then you take the square root of the result. And now do the same thing except for the y's. So add the yi's, take away the average value of y, square it, and take the square root of the result. So the sum of all these. So we've done this already, when we worked out the standard deviation. Except this time we're doing it twice because we were doing it for x's and y's. I switched to using 1 and 2, so I'll just use Roman numerals here to be different from the fact that I wrote 1 here. So the final step to get the correlation coefficient, which is denoted as R, is we just add xi minus x, or xi minus the average value of x. So kind of like we did for the standard deviation. But instead of squaring it, we multiply it by yi minus the average value of y. And then we just divide this, after we've summed, from 1 to 100, by the product of the standard deviations. And that's it. So now you know how to work out the correlation coefficient. Now in practice, whenever I've done this, I used to use my spreadsheet or some other computer program. So, I might have thousands of pieces of data, and that would be on the computer, and you just say, I do a plot, and I have the option it would automatically draw the trend line, and it will automatically it'll compute R, because it knows that that's a standard thing that people want to know. But these are the steps you follow to work out what the correlation coefficient is, and there's nothing complicated there. Yeah, you might make a slip somewhere along the lines if there are many numbers, but it's not particularly complex. The next thing I want to look at is drawing the best line, or the best fit. So the idea here is, you have your data, and the data I was looking at recently was if you can look at the global, or the average global temperature over the last 100 and whatever years, and when you plot it, it's not a constant straight line, but the trend is very much up. So if you were given this data in class, you would go, this is weakly correlated. So it's not perfectly along a straight line, but there's variations along it. Now, in this kind of case, you can just what you do is you can draw a best fit line, and again, typically a computer would just automatically do it. It would have that option, but so you just draw a line which roughly has the same trend, the same slope as the data seems to have. So you should have some dots above the line and some dots below it. So that's the first thing that that's what a best fit line is, and here we're just doing it best fit by eye. So we're doing by eye. So where you just look at it and go, well, that seems about right. If I had a ruler, this is a hand-driven, written line as opposed to with a ruler. So you'd get a better line if you did it on graph paper and you had a ruler, and then you could move the ruler around until you were happy with it. So that's the first thing. That's how you could draw a line, and then you can comment on the data and say, well, it tends to be, the slope seems to be whatever the slope of the line is, and so on. The new thing here, which we wanted to mention, was can predict. using the line. So, if I have data from 1880 to 2010, say, um, so I'll go, that's 2010 and that's 1880. So I actually have data points. So what the average temperature was for every year from 1880 till 2010. Then, using this best fit approach, I can kind of go, well, the temperature seems to be increasing, zero point 0.1 degrees every 5 years on, based on that line. So there'll be some years it'll have increased by more, some years it will have not decreased, or it will not have increased by that amount. But the trend seems to be that. Then, using that line, I can kind of go, well, if this trend continues, I'd expect in the year 2030, the temperature is going to be whatever that x is. Whatever that line that I drew goes to in the year 2030. And so that is pretty much what people do. You look at the data and you go, well, at the rate that things are currently going at, we're gonna hit the 2 degrees mark by whatever year, and so on. Now, I would add that this doesn't, to be careful. A lot of for example, if you look at, say, house prices, then what happens is you have 10, 20 years of house prices going up faster and faster, or going up at a very fast pace. Then what people do is say, well, if things continue like they have been, well then, in 5 years' time, house prices are going to have doubled or quadrupled. And so they then act, and they plan accordingly. But then suddenly the house prices crash, and they go, oh, how did that happen? It's because people do this. That when you look at a pattern, this will say that's the human brain is a pattern finding machine or whatever. That we see patterns where there are none. So there is a danger of this, of predicting the future, even though, history shows that we're not very good at it. So, warning, we can't predict the future. And there was a nice expression along these lines where they say that trees don't grow to the sky. So, if you plant a seed and you watch a tree growing, and then it's 1 foot tall, then it's 5 foot tall, then it's 10 foot tall, but it's not going to become 2 miles tall. There is trees after they grow maybe 100 feet, it stops growing. So if you were to plot the height of the tree by year, you'd be able to get an increasing trend, and then you could predict to the future and say, in 200 years' time, the tree's going to be 3 miles tall. Or if you plot your own height, you see a baby and go, oh, the baby's tiny, and then every year it gets taller and taller and taller. But the baby's not going to be 20 feet tall. You can't. So if you were to plot the data and predict using this method, you would end up predicting that the baby's going to be, 20 feet tall, which I can tell you is not going to be the case. That's actually not particularly that's not on the syllabus. but I wanted to um, throw that in because it's worth saying, and it's an important um, flaw that all the financial system and all that kind of stuff. It's based on looking at loads of data and then trying to predict, making projections of what's going to happen in the future. When history has shown that there's we're pretty good at it, but don't have that much faith, conviction, belief in these predictions. So the next thing I want to talk about is percentiles. So here, imagine you have a class of 100 people and they've all done a maths exam. Then I just put the grades, or I put the students in increasing order of the grades they got. So the first person got the lowest grade and the 100th person got the highest grade. So 100 people do maths exam, or maths, yeah, I'll say maths test. Then put in increasing order of result. So the person who, so percentiles would mean that you describe the person in terms of where they came out of the 100 people. So the person who came last would be first percentile, because they only actually, depending on which order you put them in, at times you would say that the person who came first was in the first percentile because they came in the top 1%. But you could also say the person who came last was in the first percentile if that's the order that you put them in. So percentiles would be where you put the people in the order in which they came, or some order, and you describe them in terms of percentiles of where they were out of those 100. You've seen something like this already. So the median would be the 50th percentile. So half the people are below that mark and half the people are above. Likewise, the quantiles, or quartiles, say, because it's quarters, are quarters. So the first quartile is the 25th percentile. The third quartile is the 75th percentile. So it's just a way of describing things. The last thing I wanted to talk about is using plots. So say you had one class and they got their marks ranged like this, and you had another class and their marks were like this. Well, then by just looking at the plot, you could say that the average grade, so average and the median, grade in class B higher than A, because all the marks in class B are higher than the marks in class A. So that in that way you can comment on the numerical properties, the median, the central tendency, what the typical mark is, based on plots as well as well as the numerical analysis. Likewise, if you had class A and their marks were all clumped together, while in class B they were all over the place, or there was a huge range, then you could, by looking at that plot, say the standard deviation, range, interquartile range, all those things, so the variability greater in class B than class A. That's all I wanted to say about statistics.